Welcome to our lectures on the DC microgrid and the control system. We shall continue with our stability analysis also in the DC microgrid. So, what was discussing that with the problem with the CPLD in our previous lectures. So, the DC microgrid facilitate the integration of the emerging DC renewable energy sources. That is, we have you may integrate the fuel cell, not only solar and wind or any other sources of the power, energy sources, example photovoltaic and the fuel cell, or the energy storage devices, the battery, ultra capacitor or the super capacitor, as well as modern power electronics loads by eliminating the redundant energy conversion. The development of the DC microgrid can overcome the practical issues of AC network, such as you have no problem of the frequency synchronization, concept of the PLL is missing, reactive power flow, active power flow and its control, those are all missing, ingress current from the transformer, current harmonic and other all the nasty power quality issues. You get rid of all those entities in a DC microgrid. And unfortunately, at the time of Edison, so those power quality issues was not very prominent, otherwise I am more than sure Edison would have been win the battle over the other counterpart. The electronics, so let us come to the discussion again. The power electronics based system, mostly these converters are power electronics based system, are increasingly used in aerospace, industrial and the military area because of the benefit of being many, such as higher efficiency. You may have a high frequency, high efficiency DC to DC converter, reduced size and the lower cost of the maintenance. So, if you increase the size, if you are flying, it is a cost. So, if you more compact, if you can make, so that will be advisable and has to be practiced. However, in case of this electronic based system, tightly regulated power electronics devices such as inverter, converter and the front end motor drive, AC to AC conversion, maybe in case of the AC microgrid, behaves as a constant power load. Not only those DC CPLD, this also behaves as a constant power load to the power supply and have the negative input resistance. That is quite detrimental. If you have a negative input resistance, so that is quite disadvantageous, which may lead to the instability of the DC bus. That is something we require to observe and find out the solution for the same to healthy operation of the DC microgrid. So, in order to achieve the safe and the reliable microgrid performance, its dynamic stability needs to be ensured in all the operating conditions. That is something we require to do. A typical cause of instability in the DC microgrid is the impedance mismatch. So, source impedance and the load impedance, for this I was telling that this is the maximum power theorem, please recall, and generally converters has a high input impedance like op amp and a low output impedance. That is what we want, because So, for this reason there is a problem of the mismatch between the highly damped filter to the source size and the tightly regulated converter on the load side. So, source size you are allowed to vary, because solar irradiation will change and you have the IV characteristics of the solar panel will change. But what essentially you are doing in your output? You are keeping your voltage constant, load constant, and thus there will be a buffer in between that power electronics place, ultimately that leads to the mismatch between the impedance. So, I will ensure the stability there, that is a challenge here. So, this kind of converter often referred as the constant power loads, which introduce the negative impedance characteristics in the low frequency range that tend to oscillate with the output impedance of the power supply. Again, these are the quite nasty phenomena, please understand it. The CPLD, what it does, which uses the negative impedance characteristics in the low frequency range, that means the supply frequency range, and tend to oscillate with the output impedance of the power supply filter. So, it will be sometimes maybe gives you a low frequency oscillation also. So, in practice, speed regulated motor drive and the electronic load introduces such destabilization effect, and where you will find that it will oscillate with the power supply. So, because what happened, please understand it, why there is a mismatch. You are feeding DC to AC, so you got an inverter, and what happened, this is your average power that you are supplying from the DC, and overall you have this power. This is oscillating double frequency oscillation, because when you are crossing 0, then current is very low, or if you have a quite heavily loaded, then it is almost power factor is 0.8, 0.9. So, what happened there? So, you are feeding a very less amount of power, but when voltage and current both are very close to the peak, then also what happened, you are taking huge amount of current and power. So, there will be a low frequency oscillation into the system, and that will be reflected to the DC microgrid, and ultimately capacitor voltage will have a swing, and that is what I am saying. So, it tend to oscillate the output voltage impedance of the supply filter, and this causes lot of, and again if you have a huge amount of this kind of load in the DC microgrid, you may have a ACs that you are now reading, you have a ACs that is inverter fed, essentially input is DC, because when you are running from the grid, you may rectifying it and you are feeding to the inverter. But when you already have a DC, you do not rectify it, you put it to the inverter, and so this kind of nasty phenomena will come across, and we require to stabilize the grid in those circumstances also. One of the advantage of this grid is that it is, because of its huge inertia, it is more or less stable. If you do something, it does not happen to the grid much, because in India we have a power grid due to the courtesy of the power grid corporation. I tell you, whole power, it is handling the terawatt amount of the power. So, it is quite natural that it is a sudden change in some portion of the grid does not affect, but its microgrid, if you have a huge amount of the CPLD, it is a big concern, and it is a great challenge for the power electronics and control engineer to address it. In order to provide the practical explanations of the stability phenomena, that is what I try to do in my next slide, previous slide. In DC microgrid, a voltage regulated buck converter fed through the line filter on one side and supplying a resistive load on the other side is taken for the case of the demonstration of the constant power load concept, and we shall apply the averaging phenomena and also linearize in a neighborhood. The averaging and the linearization is the most common approach for modeling of the DC microgrid. We have seen an analysis of the switching power converter in DC microgrid. Students are advised to refer my previous lecture on advanced power electronics on DC to DC converter. There this average model and linearization other aspects has been covered in details. and the models of the individual components are assembled in a full system model, which then typically broken into the two subsystems at arbitrary DC point. So, we will break it, since you know that when switch is on you have one set of characteristics equation, when switch is off another set of characteristics equation, but we just say in a different manner here. So, we have a load system and a source subsystem. One switch is on, then power is transmitted from the source to load. So, we got a source subsystem, and when switch is off ultimately capacitor has to feed the load. So, thus you have a load subsystem, and thus impedance also changes in these two circumstances. Consequently, the analytical expression are derived for the input impedance for the load, the input impedance, that is Z I, and the output impedance of the source subsystem. Each of the two subsystems are individually properly designed with a good dynamic performance. The influence of their interactions can then be studied by looking into the Zs by Zin, which is often referred to as the minor loop gain. So, that is something you have to keep in mind, that is this Zs and Zin is the input impedance. And so, dynamics of the DC power supply. Now, this is the figure 1 where it is consisting of the input filter. Why input filter is given? Because you talk about your MPPT, solar MPPT. Solar panel, you are taking power, all of a sudden if you are breaking circuit, then you are making your current 0. So, this is not allowed, and thus there will be a huge shift of the PV curve in the IV PV curve of the solar panel. So, you are operating here, you are supposed to operating here, and all of a sudden when switch is off, what happens? This is I and this is V, you moving this to this point, and that is not allowed. So, again you have to jump from this point to this point, it is not possible. And for this reason you require to put a input filter. I am coming to this point little later. So, this figure 1 shows the common bus realized by means of a power supply unit with a line filter, which is a point of the load, or in abbreviation we shall use it POL, buck converter supplying the resistive load, and is connected like this in the figure as been shown. So, you got a filter, then you got a common DC bus. This portion is common, and this side we say that it is the Zs, and other part from this side which is truncate it or the clip it by scissor, and this side we say that it is the input impedance here. And of course, you have to match this impedance, this has to be this, then only you will have a maximum power transfer to be takes place anyway. So, if there is a mismatch between these two impedances, then there is a challenge of stability. So, the input filter is used for the main functions as I was explaining. It flattens the current drawn from the supply side, that is what I was saying, taking an example of your assuming that this is a solar MPPT. So, this is the problem, all of a sudden switch is off, then current will go to 0, again it cannot track, and moreover it attenuates the high frequency variation of the input terminal of the POL converter. So, if since impedance is varying, when switch is on then impedance is something else, when switch is off impedance is something else, and thus what happened, due to that change in impedance that attenuates the high frequency variation of the input terminals, and for this reason that will act as a buffer to the source. so that it will be not affecting the change of impedance to the source. So, while providing, that is a challenge, though you require it to aid because of it. However, while providing these two input functionalities, the supply side filters also brings an additional dynamics, because in the LC you are having a step change everything, every time it will respond. So, the supply side filters brings additional dynamics which might be introduced, undesirable characteristics with the power electronics or this converter, that is the abbreviation of it, that is called POL converter, parts of loading, that is the point of load. What happened, any change in step, because you cannot expect that load will be constant, it is something the prerogative of the consumer. I switch on one light, one set of LEDs, all of a sudden I will move out one point to another point, maybe it is a automatic sensor based, then other lights are switched on. So, while load change and this dynamics, if it is not properly damped out, will give you a sustained oscillation. This is the, in a layman's language, this is the problem. So, the voltage controller of this POL converter is tuned to adjust the ratio, so that it is try to keep the voltage on the resistance constant regardless of the any voltage change of the common bus. That is something that it gives some amount of the insulation, that is voltage controller of the POL converter is tuned to adjust the duty ratio such a way to keep the voltage on the resistance constant. So, irrespective of the change in the input, regardless of any change of the voltage in the common bus. That is the task of it. If voltage may be coming down in the common bus 48 to 46, but this converter will maintain that regulated voltage to the resistive load. And what happens then, if the voltage control loop works perfectly, the voltage and therefore the power on the resistance remains a constant value, then there is no problem at all. And therefore, in case of VDC decrease, this I of this point of loading will automatically increase in order to maintain the constant power, and that is what happened, because the incremental resistance seen between the DC bus side and appearing with the negative incremental value. So, voltage if decreases, then current has to increase, and thus you have a negative resistance characteristics. Positive resistance is healthy, but if you have got a negative resistance, it has a quite detrimental value, you have to control it. So, the incremental resistance mathematically expressed can be this RIN is VDC by I dVdI of this POL, thus differentiated you get this again the same thing minus P square by I 0, and negative signs is basically representing that it is a negative resistance. So, if you have this operating point where voltage is more and thus current is less, then if you go to this operating point, very close neighborhood maybe, then what happen, you have a voltage sag and thus you move into here, then operating point will change accordingly, and you can see that del V by del I is less than 0. So, this is the problem here to adjust. So, once voltage drops, current decreases. So, from this notation, let us clarify the notation first, then only we will describe it, where VDC and the I suffix POL are the output voltage and the current of this POL converter, and P is the constant power consumed in the resistors, and IPOL is the steady state value of the IPOL. The analytical expressions for the closed loop point of impedance of POL converter is required in order to describe the dynamics of the load subsystem and quantify the interaction of the supply side. Let us see that. So, let us design the closed loop transfer function of it. Closed loop input impedance of the POL converter depends on the configuration of the load, converter's filters, loop gain and the converter control circuit. This is all the parameter will have effect on this overall closed loop performance. The POL converter impedance expressions is given by Zns equal to Rin equal to minus R by d square, where ds equal to R by d square 1 plus this transfer function will come, and where this R, L, C are the resistive load, inductance and capacitance of the converter, and D is the duty cycle of it. And please understand that we have kept this thing pretty simple. While discussing this DC converter, we have kept that it is operating in a continuous conduction mode. If you also if you try to operate this converter in a discontinuous conduction mode, then things will be pretty complicated. So, that we are avoiding it. So, that can be a very good research topic while designing the DC to DC converter in a light load in a discontinuous conduction mode, but mostly we are designing that where you have a load is increased some way, and that is a stability problem. So, one nasty aspect we have neglected, that discontinuous operation of the DC to DC converter because of the high loading. So, the loop gain Ts of the product of the transfer functions is representing different elements in the forward and the backward path of the control system. Considering the voltage regulated POL converter is shown in the figure, Ts can be represented by Ts equal to Hs Cgs GVDs by Vm. So, you get this transfer function, and thus what we can write here, this Hs, this transfer function is a census gains of the feedback path. That is a gain in the feedback path of Gc, or the plant is the TF voltage controller, and GVD is the transfer function describe the relation between the converter duty ratio and the output voltage, and 1 by Vm is the PWM voltage gain. It is nothing but a modulation index, and these quantities can be expressed to given expression as described with the closed loop form. So, 1 by Zn, that is the admittance, equal to 1 by Ns into the time delay system, that is Ts plus 1 plus Ts, thereafter 1 by Zd by 1 by Ts. So, from this previous equation 5, so we can narrate few things, and it can be seen from the above equation, the previous equation, that the impedance follows Z and S, because these are the term are at the switching frequencies. So, this will have a direct correlation. So, for this we can say that we can see that the above equations follows the ZNS at low frequency, where magnitude of the Ts, that is the switching frequency, it can be 10 kilohertz, that is 1 microsecond, maybe if it is in a switching at a level of the megahertz, but generally we operate those things, the power converter at 10 kilohertz. So, thus Ts value is 100 microsecond. If it is 100 microsecond, 1 plus 100 microsecond by 100 microsecond, ultimately this part decimates, does not have any implications. Same way, if you add up this value with the 10 microsecond, ultimately this value can be taken as a 1. So, that is what I am saying. So, this value does not have much implication. So, the high where magnitude T s is high, where JDS becomes the dominant at a high frequency, where T s drops in the magnitude. It should be noted that the Z I N S is an independent quantity in the circuit and remain unaffected by the filtering configuration at the supply side. So, that is something quite interesting to observe. Similarly, the output impedance of the supply filter Z s is independent of Z I n. So, let us revisit these equations again, and so see that. So, this will have a two term, one is Z n, another is Z d. So, and where we have a different transfer function, and this is the overall input transfer functions from this power electronics converter. And while having this, this T s, you can see that T s has an entity of H s, G C s and G V D by V m. And thus what happened. So, please recall what I am saying here, that it can be seen that from the above equation that the input impedance followed that Z n s at a low frequency, where T s is high and where Z T s become dominant. So, this part become dominant, and at a high frequency this part becomes dominant. So, there will be two characteristics, one is at a lower frequency level, and that comes into the picture. Maybe you have you are interacting with the inverters or something, or there is a slow oscillating some voltages, might be you are feeding from the wind turbine and it is generating maybe the wind speed maybe a 16 hertz, 17 hertz rectified, so that you convert it to the DC. So, there the low frequency phenomena comes into the picture, and if you have a totally DC, then also then you can say that frequency is 0, as simple as that. So, in that case this entity will be dominating, otherwise this entity at the high frequency will dominate. So, this is the takeaway from these discussions. So, while designing the performance of the power electronics converter fitting this kind of CPLD, we require to design with the proper consideration, and the filter has its effect, and that all has to be taken into the consideration by the closed loop transfer function. We shall continue to discuss with the stability issues of the microgrid in our next class also. Thank you for your attention.